All right, today we're diving into something really cool, the mathematical blueprint that teaches an AI how to make smart choices, not just for right now, but for the long game. We're talking about Markov decision processes, or MDPs. This is basically the rulebook for teaching a machine how to think ahead and win. So let's get right to the heart of it. It's pretty easy to grab an immediate win, right? But how do you teach a machine to be strategic, to understand that maybe taking a small hit now could lead to a massive payoff later on? That's the exact puzzle that MDPs are built to solve. And to really see how it works, we're going to follow a simple little agent on a mission. So to make this all feel a bit more real, let's meet our little hero, a robot. And its one big problem: it's stuck in a maze and needs to find the absolute best way out. This robot's dilemma is going to be our guide through this whole thing, and it'll show us how these kind of abstract ideas actually create what looks like real intelligence. Okay, so this is the robot's entire universe. It's just a simple 2x2 grid. It starts up here in the top left. The big prize, the goal, is in the bottom right, and that's worth a sweet plus 10 points. But there's a catch. See that obstacle in the top right? Land there, and you get a penalty of -5. Oh, and one more thing. Every single move it makes, doesn't matter where, costs 1 point of energy. So the big question is, what's the smartest path to get the biggest score? Now, before our robot can even begin to solve this thing, it needs a way to understand its world, right? It needs a language. And that's exactly what the 5 core parts of a Markov decision process give it. Think of them as the building blocks that let the robot see its environment, its options, and what happens when it makes a choice. First up, we have the state, which we just call S. A state is really just where you are right now. For our little robot, it's super simple. A state is just the square it's standing on. That's it. In this whole maze, there are only 4 possible states. Okay, next up, actions, or A. This is just the list of all the possible moves the robot can make. So from any square, our robot can go up, down, left, or right. These are the only tools it has to get around. So we know where the robot is and what it can do. But what happens when it does something? That's the transition function, P. It's basically the physics of our little world. It tells us the chances of landing in a new spot after taking an action. Now, for our simple maze, things are really predictable. It's deterministic. That just means if the robot decides to go right, it goes right, 100% of the time. No weird surprises. And of course, there have to be consequences, right? Carrots and sticks. That's the reward function, R. It gives the robot instant feedback for its last move. And this is where those numbers we saw earlier come back into play. Land on the goal, you get plus 10. Hit the obstacle? Ouch, that's -5. And every other move, it costs you 1 point. This reward system is what drives the entire learning process. Last but not least, and this one is super important, we have the discount factor, or gamma. You can think of this as the robot's patience level. If gamma is close to 0, the robot is really short-sighted. It only cares about what's good for it right now. But if gamma is close to 1, like the 0.9 we're going to use, it becomes far-sighted. It's willing to make a sacrifice now if it means a bigger reward down the road. Okay, so let's recap. Our robot now gets the rules of the game. It knows where it can be, what it can do, what will happen, and what's good or bad. But how does it use all that information to come up with the best strategy, the best master plan? That's the next big step. What we're really looking for is what's called an optimal policy. You'll see it written as the Greek letter pi. A policy is just the robot's complete game plan. It's the playbook that tells it exactly what to do in every single situation. If you're here, do this. If you're there, do that. Our whole goal is to find the absolute best version of that playbook. But to find that perfect playbook, we first have to figure out how valuable each square really is. And that's the job of the value function, or V of S. Now here's the key idea. The value of a square isn't just the points you get for landing on it. No, it's the total reward you can expect to get over the long haul if you start from that square. It's about the future potential that square unlocks. Which, of course, leads to the big question. How in the world do you calculate that? How do you figure out the long-term value of something when you don't know the future? The answer is a beautiful, powerful piece of math called the Bellman equation, named after the brilliant mathematician Richard Bellman. I mean, think about it for a second. To know how good the starting square is, you need to know how good the next square is. But to know the value of that square, you need to know the value of the one after it.
It feels like this impossible circular chicken and egg problem, doesn't it? Well, this is where the pure genius of the Bellman equation just shines.
The Bellman equation breaks that loop with a stunningly simple idea. It basically says this: the value of where you're standing right now is just the immediate reward you can get plus a slightly discounted value of the best place you can go next. See how that works? It connects the value of a square to the values of its neighbors. It's brilliant. And this is what that idea looks like as a formula. Don't let the symbols intimidate you. All it's saying is exactly what we just discussed. The true value of this spot equals the reward you get from your best move, plus the discounted value of where you end up. That's it. This elegant little equation is the engine that's going to solve our entire maze.
Okay, enough with the theory. We've got our maze. We've got our secret weapon, the Bellman equation. So let's put it to work and watch how our robot actually solves this thing.
The process we use is called value iteration, and it's actually pretty straightforward. Step 1, we just guess. We say every square is worth 0. Then, step 2, we go through every single square and update its value using our Bellman equation, based on the current values of its neighbors. And then we just do it again, and again, and again. We keep repeating this loop until the numbers stop changing much, until they've all settled down. And after running that process for a while, this is what we get. The values have settled. Now, the goal square itself isn't worth 10, it's worth 100. But hang on, the squares next to the goal are also worth 100. Why? Because you're just one optimal move away. Now look at the start square. It's valued at 89. Where did that come from? Well, the best move from start is down. That move costs you 1 point, and it lands you on a square worth 100. So it's -1 plus our discount factor, 0.9, times 100. What does that equal? 89. The equation has found the true long-term value of being in that starting spot. And now for the easy part, the grand finale. With these values, finding the best move is a piece of cake. The robot just has to look around and pick the move that leads to the best outcome. So from the start square, it can go down to a square worth 100, or it can go right into that nasty obstacle. Well, we just calculated that going down leads to a total value of 89. Going right, that's an instant -5 penalty. The choice is obvious: go down. And by doing that simple calculation for every single square, we get our final optimal policy. The maze is solved. Okay, so our little 2x2 maze was, a nice, clean sandbox to play in. But the real world, well, it's a lot messier. It's way more complex. So before we finish up, it's really important to touch on where these classic MDP approaches start to run into trouble. Yeah, the biggest problem by far is something called the recursive dimensionality. Our maze had 4 states. 4. The game of Go, it has more possible states than there are atoms in the known universe. You can't run our little value iteration algorithm on that. And in the real world, you often don't even know the full state of things, or your actions aren't just up, down, left, right, they're continuous, like turning the steering wheel. These are the kinds of huge challenges that require much more advanced techniques, but they're also built on this same MDP foundation. But even with all those huge challenges, here's the main takeaway. Markov decision processes give us the language, the fundamental logic for any kind of intelligent planning. States, actions, rewards, the Bellman equation, this is the bedrock. It's the essential blueprint that almost all of modern reinforcement learning is built on top of. So I'll just leave you with this one final thought. We just watched this framework find the perfect path through a tiny maze, but the core ideas are exactly the same, whether you're navigating that maze, or managing a global supply chain, or creating a new drug, or controlling a whole fleet of robots. So the real question isn't about the maze anymore. It's what other incredibly complex, real-world paths are we going to ask these algorithms to solve for us next?